free online that make merge.
Yeah.
Like they should, like some of them it'll put it as like a plus and then the arrow and stuff. But depending on what perspective you're taking, it might just be this is what's the main focus, and then that's like a sub thing. That's why it's over the arrow.
Yeah.
It's not your main focus.
So I wanted to give you guys kind of an example of some things. This is not the best example, but I forgot to look some things up. When we talk about an organic reaction, we are describing it as a synthesis, which means what? Sorry? Combination? Oh, okay. Making something. Yeah, to synthesize is to create. I mean, are you really creating? Because in reality, you're usually mixing. Sometimes you're actually removing. You're not combining things together, but you're using two things to pull something off of something else. But you do create something new from something that you had before. This is one of the reasons on your midterm I had a question that said, look at the reaction below. What spectroscopic technique would be useful in distinguishing these starting materials from the products? You want to make something new, and you want to prove that you have made something new at the same time. Not all syntheses are one step long. A lot of times you want to create something, you need to add multiple steps. So, how do you show multiple steps if you just want to show it as one transformation? We were having this conversation about substrate as well. You could just as easily refer to substrate as reactant or reactants or starting material. But I know that some of you think substrate as a growth media, right? You want to grow corn. Sorry, I was just home in Wisconsin. You want to grow corn knee-high by the 4th of July, you need some fertile soil. You need good substrate in there. You want to do a culture, you need to have substrate. I don't know. Enzymes react with a substrate, a specific substrate. So there's something about reactivity when you think about substrate. I'm not necessarily going to use the word substrate a lot. I'm actually going to use the word starting material the most. But I do want you guys to recognize if you think of substrate as meaning something else, recognize that you think of that so that you can create a place for a new definition, reactive. What we see here is actually several multi-step syntheses. And you'll see that this starting material is being transformed by the end to be this final product. But here's just one synthesis, which actually is two steps. So notice that the reaction arrow, I'm going to put SM, for starting material. And I'm going to put P for products. Do you think that what's on top is the reagent and what's on bottom is the solvent? Not so much, because there's these numbers that are indicated. First, I need to add reagent A. Second, I need to add reagent B. And this can go down as long as you would like it to. 1, 2, 3, 4, 5. What needs to go on the top? What needs to go on the bottom? Nothing. All of it could go on the top. All of it could go on the bottom. You could put the first two on the top, the bottom three on the bottom, first three on the top, bottom. It doesn't matter. The arrow is just a place to say, I'm taking this, turning it into that, and this is what I'm using. When the arrows are present, it distinguishes each individual step. So, I want to give you guys kind of a crude analogy. but I think it will make a little bit of sense. When I wake up in the morning, by the time I get to school, that is my starting materials product. Deal? So I wake up in my PJs, and I show up in my whatever this is. How many different things need to happen? Well, I need to remove my PJs. I need to put on my socks. I need to put on my pants and my shirt. Maybe those can happen in the same step. But then I need to put on my shoes. Can I put on my socks and my shoes in the same step? It needs to be first socks, then shoes. I can't put on shoes, then socks, and I can't say put on shoes and socks because it matters what order they go on in. It has to be first shoes, then socks. In the same way, it has to be first all of my clothes, then my shoes. It can't be shoes. The order does matter. So these numbers matter. Having them missing isn't okay. But in the way that we saw yesterday, where you have a starting material and a product, and it's just we call it a one-pot synthesis. Just mix everything together, and the reaction goes the way you want. And you have maybe a reagent and a solvent, maybe multiple reagents and solvents. All those get mixed in together. What if that becomes just one of these steps? Where do the reagents and the solvents go? They just all go onto the same line. So we could say reagent A plus solvent A. We could say reagent B plus solvent B, etc. Does that make sense? The arrow is one of the most confusing places for a beginning organic chemistry student. It doesn't mean anything. And in the same way, somebody was mentioning this, anything that's written over the arrow could just as easily be written with a plus sign next to the substrate, next to the reagent. It's only written over the arrow to draw your attention to something specific. So there's a reaction that we'll learn more about towards the end of the semester. It's called a Diels-Alder reaction. And it is a type of cycloaddition. You can take, this is the simplest form of the type of reagent. You can take a diene, react it with a dienophile, and you make a 6-membered alkene ring. You can show it like this. A plus B reacts to form C. But you could also show it with either one of those reagents over the reaction arrow. And you draw your attention to what you're interested in. So maybe I have synthesized this in a previous step. That's why I want it to look more important. I want it to look like the substrate. And maybe I don't want to just finish there, but I want to do first a Diels-Alder and then a halogenation reaction. Now I can save a little bit more space, skip on the intermediate product that's isolated, and just show the overall product that I want to isolate. Everybody does things a little bit differently. Some people like bond line structure in their reactions. That's how I set up my problems. Some people like condensed molecular structure in their problems. That's what you'll see on your PLO assignments. Ron Valcarce uses a lot of condensed molecular structure. Some people use those abbreviations, like instead of ethanol being written as bond line or condensed, ethanol can be written as an IUPAC abbreviation, ET meaning ethyl, OH for the alcohol. So you can see all these sorts of variations. Oops. Okay, so that's kind of an idea about organic reactions, is this multi-step reaction. Another important thing that we'll be talking about is called retrosynthesis. In retrosynthesis, you have a compound of interest, but you are not reacting it with new compounds. Instead, you want to figure out how you can build up to that. So the way that's often portrayed is your product with this thick arrow pointing at the starting material. A reaction arrow says starting material goes to form a product. A retrosynthesis arrow says products that come from a starting material. What this requires you to do is look at the functional groups in the molecule you're interested in. Think about reactions that you have learned that create that functional group, and decide what functional group was needed before it and what reagents are needed to get there. Questions about this at all?
Does that relate in any way to equilibrium reactions, going back and forth?
No, it doesn't. There is something called the microscopic, the principle of microscopic reversibility, which says that anything that can go one direction should be allowed to go the opposite direction, which essentially says everything is an equilibrium. But that equilibrium might be 1 quadrillion to 1. That equilibrium might be 10 to 1. That equilibrium might be 1 to 1. So there are some reactions that we say are irreversible. They're technically not irreversible. It's just that the energy required to reverse the reaction might actually cause any other reaction to occur. The idea is that as soon as your bonds are at a tipping point, your bonds are forming and your bonds are breaking. If it can tip this way, then it also has the energy to just tip backwards. And if it can go from one thing to the other, it should be able to reverse as well. Okay. Actually, we're not going to look that much at equilibrium. We should say that everything, all of the reactions we learn are in equilibrium, but it's just, we're interested in making a product. Equilibrium is often a reason why yield is not 100%. You take 1 mole of A, react it with 1 mole of B. By the way, it's not always true, but many organic reactions have 1-to-1 stoichiometry. So you will not see stoichiometry used often this semester. It's often 1-to-1, and therefore it's implied. But we're not going to show the equilibrium arrow because we're interested in one direction. But if you have 1 mole of A and 1 mole of B, and you only get 0.8 moles of C, it's probably because equilibrium kept you from pushing the reaction all the way forward.
Yeah, so if we ever do like retrosynthesis, will different energies play a role in what starting material we end up with, or is it pretty universal?
No, energy level won't matter too much. The other thing I do want to say about equilibrium, though, we often don't explain the stoichiometry, which means we don't say that if we have a limiting and an excess reagent. It's more often assumed that whatever reagent is over the arrow is an excess reagent, and the substrate is what we want fully consumed. I can get rid of an excess reagent, but what do excess reagents do? They help shift equilibrium towards the product due to whose principle? Yeah, there you go. You memorized some dead guy's name.
It's a fun one to say.
That's right.
You know, you can pretend like you're smart.
That's true.
Oh, Le Chatelier.
French. So the equilibrium principle, Le Chatelier's principle, says if I have an excess reagent, I can drive more products. It also says if I can remove the products as they form, I can drive the reaction to form more products. And organic synthesis takes advantage of those in different ways. in the lab, but on paper, we don't always express it.
How would you recognize like intermediate catalysts on the arrow?
You don't have to. Some people will put, for instance, there's a catalyst that we'll use that is palladium on carbon, charcoal. And some people will put next to a catalyst, parentheses, cat. What that means is not they're emphasizing it's a catalyst. The audience is assumed to know it's a catalyst. What that means is that they've added a catalytic amount. Catalysts are not consumed by a reaction, correct? Which means a catalyst change how a reaction proceeds. It changes how the bonds break and how the bonds form. Usually adding more steps of bond breaking and bond forming, but overall lowering the activation energy, making it easier for a reaction to proceed, less energy required, quicker reactivity. But you don't need a lot of catalysts. You don't need a stoichiometric amount because it's never consumed. You need a catalytic amount, 10% of the stoichiometry typically. So you can indicate that something is there in catalytic amount by adding cat, but it's not required. It's more so that you will know what's a catalyst. And I'm going to introduce you to a lot of reactions. So I will explain to you what is a catalyst and what is a reagent. Okay? Some other terminology that I want to talk to you guys about when it comes to reactions. We are going to look at intra and intermolecular reactions, meaning a reaction that takes one starting material and reacts it with itself versus a reaction that takes two starting materials and reacts them together. There's a reaction that I saw while I was TAing in grad school that I thought was pretty interesting. Actually, I did forget the molecule, but I think I can make something work. I'm sorry, I'm going to shorten my carbon chain by one position. So this is 1, 2, 3, 4, 5 carbons long. It's got a thiol, a mercapto. It's got an alcohol, a hydroxy, and it's got an alkyl bromide. So if this compound is reacted with sodium hydroxide, that is an acid-base reaction, will occur first. The first question becomes, what acid will be deprotonated? The alcohol or the thiol? Why the thiol? It's larger. Has a lower electronegativity, but it's in the same family as oxygen, and it's larger, so it's more acidic. This is a karyotrend. So the thiol, being more acidic, gets deprotonated. That turns the thiol into what we call a nucleophile. It's a Lewis base. It now has excess electrons that it can donate. And carbon 5 is what we call an electrophile. It has a partial positive and a bond that is easily broken. So it can take new electrons and give away its electrons. What this does is it creates an intramolecular product. So here was carbon 1, 2, 3, 4, 5, and I have a byproduct, sodium bromide plus water is formed. So that's a 6-membered ring with a sulfur in it. Notice that the alcohol is still there, and I have done something that I call mapping my carbons. So I numbered the carbons in a specific way in the starting material. I numbered them in the same way in the products. And I can see that carbon 1 still bonded to the sulfur. Carbon 2 still bonded to the alcohol. But what has changed is that the sulfur is also bonded to carbon 5. Carbon 5 has lost its bond to bromine. Intra or intermolecular reaction? Inter in the first step, hydroxide deprotonates, okay. Intramolecular, after the sulfide attacks the alkyl halide and creates the ring. A lot of ring-forming reactions, not all, but a lot of ring-forming reactions happen from intramolecular reactions. Intramolecular reactions happen very quickly because the nucleophile and the electrophile, the thing that wants to donate electrons and the thing that wants to find electrons, the magnets in our reaction are looped together. They have all of these conformational rotations that they can go through where they can find each other and react. Intermolecular reactions are slower because those two molecules have to find each other in the sea of solvent. And once they find each other, then they can react. So here's an intramolecular reaction. Let me give you an intermolecular reaction. Here, I have an alkoxide, that is a deprotonated alcohol, and an alkyl halide. And I form an ether, but it's two molecules, so I keep a linear chain.
Are we going to need to balance reactions as we go?
No, you really won't have to do much balancing. I do want you to pay attention to what byproducts are, so I'll draw your attention to that as we talk about them.
So the 1Br on the left and the 2Br on the right doesn't matter for our purposes.
I don't see 2Br anywhere on the...
Did you not write
I think
BR
it's
two
a
in front of the
comma.
Oh, I see, yeah. NABR and comma,
Oh, okay. My bad.
H2O. Thank you.
So in that first reaction, the NaOH, the Na dissociates and attaches to the bromine, the bromine, and then the OH hydrogen bonds to the H, and that's the intra. And then
The OH minus does not hydrogen bond to the H.
it doesn't.
It does acid-base chemistry. It covalently bonds to the H.
And it's
Hydrogen bonding isn't just an attractive force. What it does is it forms a bond.
so like how do you know that it creates that ring?
We're going to talk more about it. And we're actually going to talk about the classification of these reactions. What changes happened and how do we label that? Yeah. So it's okay for now. Don't worry too much about it.
So in intra, you usually don't like add anything, you might lose something. But
Sure.
in inter, you might add or change something about the beginning.
It is a little confusing, and you guys kind of hit it on the head. A lot of intramolecular reactions still have some other reagent. But at some point, one part of the molecule will react with another part of the molecule. And they will come together to typically form a ring. Although I did show you an intermolecular reaction here that also forms a ring. So many times intramolecular reactions form rings. Sometimes they don't. And some intermolecular reactions form rings too. But an intramolecular reaction means there are bonds forming or breaking between two parts of the same molecule. Is that okay? First, when I answer Brett.
So along with that, like, so the first one's intra, so would that mean like the second one on this one would be inter?
That's right.
Okay.
Intra, inter.
Okay, so I have this analogy in my head, but tell me if I'm off with this. So I'm thinking inter, like international.
Yep.
Multiple countries.
Yes.
And intra, like states within one country, like Utah and California, right?
Yes.
And if you're doing a deal between Utah and California, that's intra,
That'd be an intranational deal.
intranational.
That's true.
It's one molecule reacting with another part of the same molecule.
So I like to say interstate. Interstates span multiple states, except for Hawaii, Alaska, and some interstates are localized to one state. So they are misnomers. Those would actually be called intrastate highways, which then otherwise most other highways are intrastate highways. But the best intra that I knew was in college, I played intramural sports, which meant teams playing other teams that were just part of the same college. Intercollegiate sports would be one college playing another college. Intramural sport, I'm not sure what mural means there, but intramurals were just all pointers playing each other. Intra, within, inter, outside. So a reaction that happens within a molecule or a reaction that happens between two molecules. I do want to say this is probably the first chemistry class you would have seen where an intramolecular reaction happens. I don't think general chemistry ever involves intramolecular reactions. But general chemistry doesn't typically have these long carbon chains either. This is really, I want to ask you guys, is this molecule stiff or like slinky-ish? Yeah. I think of it as a shoestring. Or if you remember on the first day of class when I brought in that double-edged magnet, if you had that, it'd be kind of like this. You just have to play that game where your two magnets finally run into each other. That's going to happen pretty quickly. But if I have a magnet over here and I give Zubaida a magnet over there, and we just try to throw our magnets at each other, when are they going to hit and actually form a bond? We're going to have to keep trying. Even if they get close, they might not hit each other with the right velocity or the right orientation. So intramolecular reactions happen very quickly. Intermolecular reactions are more challenging. It's a game of odds. It's statistics. Okay, good? All right. I want to look at classes of organic reactions. First, we'll look at addition reactions. The trend around addition reactions is that a pi bond is consumed. Or perhaps more than one pi bond. Oftentimes what this means is that two groups are added across a pi bond. So if we were to look at kind of a generic example here, and I have this alkene pi bond, then I can react the alkene with reagent AB, and the pi bond is consumed, A and B add across. We're going to look at a lot of addition reactions next week. and then a few more the week after that. Next week, we're going to look at just addition reactions of alkenes. Technically, there are all sorts of addition reactions. So let me give you a few examples. One of the addition reactions that we'll look at next week is called hydrogenation. I add hydrogen across a pi bond. I could also do bromination, where I add Br2. Chlorination, where I add Cl2. We're going to look at halohydrin, haloether. Hydration, where I add H and OH across the pi bond. In OChem 2, you learn a lot about acyl addition reactions. What functional group do I have in my starting material there? Ketone. Is this a one-step or two-step synthesis? It's 2 steps compared to the first addition, which was 1 step. Doesn't matter that the top and bottom were both consumed. The numbers tell you everything. And the product. How could we best describe the product that forms in this addition reaction?
Okay, IUPAC name.
Now, a IUPAC name would work. It's protonated. Yeah. Tell me what has been. Well, sorry. Go ahead. Yeah, what were you gonna say?
Is it one methanol?
That's not one methanol.
One methyl, one methanol. No, not
One methyl cyclohexanol.
Oh, yeah, that's cyclo.
What I was looking for was actually a tertiary alcohol. How would you have known that? But that is a tertiary alcohol, correct? Okay, in this first reaction, what has been added across the alkene? H and H. In the second reaction, what has been added across the carbonyl? Methyl and hydrogen. The carbon gains a bond to carbon, the oxygen gains a bond to hydrogen. Sometimes it's not obvious what has been added, especially when it's hydrogens, because we are just so used to ignoring all of the millions of hydrogens that we look at all semester long. But they are being added across there. Okay, good? This is alkene addition. If you're interested in knowing more like specifically how we would classify this. The second one is called acyl addition. The acyl there implies the carbonyl. Acyl is just our term for carbonyl.
In this second one, is that a lithium there with the CH3?
It is.
So are we just, it just kind of disappears? Or it's consumed?
Okay, it's not a catalyst. We're just not interested in it. What I would say is it's a byproduct.
Okay. So this goes back to the balancing question earlier. We don't necessarily have to have the exact same thing.
Correct. Although, if we look at the reactants, by the way, where do the reactants stop? Is this a reactant? Is this a reactant? It's not reacting? Sorry. Thank you, Cameron. Yes, good point, good point. Or bad point, rather.
It's a trick question.
Is this a reactant? Yeah, anything that's on or before the arrow is a reactant. So what is the net charge of the reactants? +1. So what should the net charge of the products be? So there is a byproduct, just based on what I've put, there is a byproduct of Li+, lithium ion. In reality, H+ is not a reagent you can get in the lab. So maybe you have like HCl, and then your byproduct would be LiCl, lithium chloride. I will focus on byproducts throughout the semester because I do think it helps you connect where everything is going. But mainly our main focus is substrate. All right, good? Yeah? Second class, elimination. Elimination creates a pi bond. Now, this is incredibly generic, so I don't want you to assume that in every elimination reaction, the two things that leave create their own product. That's not true. It's generic. What it is saying is that two things leave two of your atoms, and a pi bond is created. Not to mention, elimination can happen multiple times. Just like how addition can happen multiple times. If I have multiple pi bonds, I can consume those multiple pi bonds. And if I have multiple things that can leave, I can create multiple pi bonds. So elimination is what we'll use in Unit 5 to create alkenes. We'll review it as well when we look at alkynes in Unit 5. But elimination is not reserved just to alkenes and alkynes. Elimination happens with any pi bond. So let me give you an example. This would be an alkyne synthesis. To 2-dibromobutane, excess of sodium amide. Notice there I did kind of imply the stoichiometry. There is an excess reagent. And the product is 2-butene. Were pi bonds created? How many? 2. How many eliminations occurred? 2. What are the byproducts here? What has been eliminated? Br has been removed and H's have been removed. So 2 Brs and 2 H's. We could refer to this as a dehydrohalogenation. I've removed hydrogen and halogen. The base is actually helping me out here. So if I'm looking at my products, NH2 minus is taking hydrogens to make NH3, and it does that twice. The sodium ion is balancing the bromide ion, and that happens twice. Those would be byproducts in this elimination reaction. Intermolecular or intramolecular? Intermolecular. Because there's not really, I told you earlier, one part of an atom bonds with another part of an atom. Typically not like this, though. Not next to each other. Not in elimination reactions. All right, well, here's another one that is very common. This is oxidation of alcohols. This is one that we won't see until OChem 2. If I take ethanol and I react it with a reagent that we shorthand as PCC, then I can make acetaldehyde, ethanal. Has a pi bond been created? Yes. What has been removed? 2 hydrogens. Now, in your body, enzymes perform this dehydrogenation. Enzymes remove 2 hydrogens to turn ethanol into acetaldehyde, which is toxic. It's not something you really want in your body. But chemists would use PCC, which is pyridinium chlorochromate, not an enzyme at all, not a catalyst either, but instead uses toxic transition metals.
Here, quick question, on the alkyne synthesis, those bromines, so they're connected to that carbon, but wouldn't that be an ionic bond to the carbon?
No. Carbon to bromine is not an ionic bond. It's very much covalent.
Oh, gotcha.
Metal and non-metal. Metal and non-metal. That's ionic. Metal and non-metal. That's ionic. Non-metal and non-metal, covalent. Non-metal and non-metal, covalent.
So even though, like, they could be on opposite sides, or, farther apart, but they have to be opposite like that to be non-metal versus metal.
Correct. Got to be metal and non-metal. Actually, this is a metal and non-metal bonded to each other, except it's often described as a covalent bond. But it does behave a little bit like an ionic bond, like it would be expected to.
So what's the biggest giveaway of intra or inter?
Just the products, really. If you're looking at an inter or intramolecular reaction, the products kind of tell you. All right, last major class, the one that we're going to, the last one that kind of fits with these three, substitution. Best way to describe this is that typically a carbon atom swaps groups. Carbon atom has a bond to something, now it has a bond to something else. A lot of ways that we can write this as a generic reaction. Oops. I'm just going to have carbon bonded to Y, swaps for a bond to X. Kicks off Y as a product. There's a lot of things wrong with my generic reaction here. For instance, substitution reactions often have nucleophiles that are negatively charged, and that would kick off something that is negatively charged. But again, generic, what is X, what is Y? It's not an element. So it's just showing that a bond leaves, a bond forms. What kind of reaction is this? Was a pi bond consumed? Was a pi bond created? Was a group swapped? Carbon 5 was bonded to bromine. Carbon 5 is bonded now to sulfur. What kind of reaction was this? Was a pi bond created? Was a pi bond consumed? So then what group swapped? Wow, that was really cool to hear. Thank you. I couldn't make out anything, but I liked it. Carbon to bromine bond broke. Carbon to oxygen bond formed. Swapped out those groups on this methyl carbon. You could also say that oxygen swapped its ionic bond to sodium for a covalent bond to carbon, but this is organic chemistry, so we're often focusing on the carbon atom more so than the oxygen atom.
Is it just one carbon making a swap that makes it a substitution? Or is that too simplistic of a way to think about it?
So, I mean, technically, anytime you had one bond that left and was replaced by another bond, whether that's to an oxygen or a nitrogen or whatever, that is a substitution reaction.
But that wouldn't exclude the elimination or whatever number one was. Because that deals more specifically with the pi bond.
Yeah.
So we can swap carbons.
swap bonds.
between a carbon. But that doesn't automatically qualify it as one of the others.
Well, I mean, that sounds like a different class, right? If you're just swapping bonds and you're not consuming a pi bond, you're not creating a pi bond.
Right.
You're substituting. Yep. Let's do a couple of reactions. I know I just had those there. We're going to be looking at terminology this semester. We'll explain it in Unit 5 a lot more. But this is what we call, I want to give you an SN1 reaction. Again, not something you need to recognize what SN1 is yet, just a preview. Pi bond created, pi bond consumed, so it must be substitution reaction. There is something odd happening though, right? The carbon that lost the bromine isn't the carbon that bonded to the oxygen. This is the result of something that we call a carbocation. You guys remember that word? Positively charged carbon, missing an octet. Carbocation rearrangement. The carbon bonded to bromine loses its bond before it takes a bond to oxygen, which means it loses its bond and becomes a carbocation. We're going to learn more about carbocations this week. And we're going to learn that not all carbocations are equal. Some are more stable. And so other groups are willing to shift with their electrons and create a new hole, create a carbocation where they left from that is a more stable positive charge. And that results in structural rearrangements. Very awesome artifact of organic chemistry. I want to show you guys also acyl substitution. This is something I'll be teaching my OChem 2 classes, my OChem 2 class next week. And it's something that the OChem 2 lab will be doing in lab tonight and tomorrow afternoon. Pi bond consumed, pi bond created. Where is the substitution? Not in alcohol. You guys watch The Good Place? Janet, not a girl. She always says that. Forget her boyfriend's name. Jason. Jason's like, "You're such a good girl," and that's not how he says it. And she's like, "Aw, not a girl." Not an alcohol. But I see what you mean. I get it. Carbon to OH bond breaks, carbon to Cl bond forms. Substituted. Now, here's a really cool thing. The process of this reaction is not one step. Instead, it's actually an addition reaction that creates something like this. And this is bonded to the rest of this group. And that's positively charged. Sorry. A lot going on. You don't have to copy this down because it's not going to be on your test. That's an addition reaction. Would you agree? Why? Pi bond was consumed. There's no more pi bond. And then it's followed by what? It's followed by the creation of a pi bond. Elimination. So this acyl substitution is actually acyl addition followed by acyl elimination, essentially. There's another one that, again, you won't see this until OChem 2, but I don't see why there's no reason for you not to see it now. That is substitution on aromatic carbons. I'm getting really used to drawing my little circle in the middle, which is a bad way to do it. If I take benzene and I react it with elemental bromine in the presence of a catalyst, iron 3 bromide, I can create bromobenzene. And this actually happens through the similar process of an addition reaction that follows, or that is followed by an elimination reaction. So the substitution that you and I will cover this semester in Unit 5 is mostly like this type of substitution, SN1 and SN2, which are very different from acyl substitution and very different from aromatic substitution. So this is sometimes called like SN, actually I don't think it is, but acyl substitution is very common. This is often called SNAR for substitution at an aromatic carbon. They can happen by different means, but what you're analyzing is the overall change. Checks out? You guys okay with that? All right. These are the main classes. When you look at a reaction, this is what I want you to think about. But are you guys okay if I erase the board? You got all these reactions down? You guys see why I want you to get good at drawing structures early on in the semester now, right? I mean, you're going to be drawing structures the rest of the summer. There are some subclasses that I want you to be familiar with. The issue here is that these are two different classes. I'm calling them subclasses because they're maybe less relevant or they're more specific. But really they can be combined. First of all, oxidation, which really just means you increase bonds to electronegative atoms. Relative to what? Carbon, typically, because we're in OChem. So carbon increases bonds to electronegative atoms. Okay, well, I've actually got an example for you there. Ethanol reacts with PCC You don't see the increased bonds when it's in bond line form, do you? But carbon loses one bond to hydrogen and increases one bond to hydrogen. So oxidation in this case is what? Elimination. This is an oxidative elimination reaction. But if I took an alkene and I react it with elemental bromine, I have increased the number of bonds to more electronegative atoms. I have oxidized those carbons by doing addition. So addition is not always oxidative. Elimination is not always oxidative. They just describe what the carbons are bonding to over the course of a reaction. Are you guys okay then with calling it a subclass? They help modify whatever class of reaction you have. Then, of course, the opposite would be reduction. This is where you increase bonds to less electronegative atoms. Maybe it's important to realize, though, that you can perform a reduction by simply decreasing bonds to more electronegative atoms. Oxidation. Increase bonds to more electronegative atoms and or decrease bonds to less electronegative atoms. Reduction. Increase bonds to less electronegative atoms and or decrease bonds to more electronegative atoms. So, I would actually remind us of the hydrogenation example that I gave earlier, where cyclohexene is turned into cyclohexane. And I'm not quite sure that I can think of a reduction reaction that proceeds only by reducing bonds to more electronegative atoms. So I'm going to leave us there with that one. Okay, questions about addition, elimination, substitution, oxidation, reduction. I think that one thing I could do to help you, this is not going to be test questions for you guys. So I could show you how the oxidation state changes. To calculate an oxidation state, which is really just a comparative measure. Oxidation state doesn't really tell you anything. It just compares one atom to another. You give a carbon, or any atom, a +1 for every bond to an atom that is more electronegative than it, and a -1 for every atom that is less electronegative than it. So in ethanol, carbon has 1 bond to carbon, 0, 2 bonds to hydrogen, -2, 1 bond to oxygen, +1. That's an overall -1 oxidation state. In the product, carbon has 1 bond to carbon, 1 bond to hydrogen, and 2 bonds to oxygen. So that's -1 and +2. That's a +1 oxidation state. Oxidation is a loss of electrons, increase, a more positive oxidation state. Electrons are negative, so a more positive oxidation state is a loss of electrons. Oxidation. Here, carbon is bonded to carbon, carbon, and carbon 3 times. And then it's bonded to hydrogen once, so the carbon gets a -1. In the product, carbon is bonded to carbon twice and hydrogen twice. That's -2. Oxidation state has become more negative. Electrons are negative. Reduction is a gain of electrons. Okay? So, you could look at a lot of the other reactions that we saw and you could say, is this oxidative? Is it reductive? Is it neither? Sometimes one carbon is oxidized and the other carbon is reduced, and overall the molecule is neither oxidized nor reduced. That's okay. It is okay for redox reactions to kind of counterbalance each other across 2 atoms. All right, I want to give you guys a break. Let's take a quick 5 and then come back in and keep talking about different terminologies in these reactions. Deal? No. The 1 and 2 in SN is referring to the reaction kinetics.
Okay.
First order or second order.
This might be a dumb question, but like you were saying, like the C to C is a -1 bond or +1? 0? Okay.
No difference in electronegativity between carbons.
Okay. And then so the C to H was the negative one that you were talking about?
That's right. Yep.
Okay.
Because carbon steals electrons from hydrogen. So carbon gets the -1.
And then the O to carbon oxygen to carbon was the +1?
because oxygen steals electrons from carbon,
Okay.
puts a +1
So
on carbon.
we're looking at just carbon when it comes to that. Like if it is.
Well, we are in organic
Yeah.
chemistry.
Yeah,
Exactly.
Okay. So if carbon's taking its negative, if carbon's giving its positive.
And redox is always equalized.
Mm-hmm.
Something that is reduced is oxidizing something out to something else to an equal and opposite extent.
Mm-hmm.
So when I say that carbon takes on a -1 from each hydrogen takes on a +1.
Yeah. So it's kind of like with every reaction, there's an equal and opposite reaction.
Almost exactly that. Yep.
Okay. That makes sense.
Which means that if you actually sum up all of the oxidation states of every atom in a compound, it should equal the charge of the compound.
Mm-hmm.
So ethanol is net neutral. The carbon on the left is a -3. The carbon in the middle is a -1. The oxygen is a -2. -3, -2, -1, that's -6. And there are 6 hydrogens that are each +1. That's +6.
Mm-hmm.
-6 and +6, net neutral,
Mhm.
0. Look at the reduction. Hydrogen has an oxidation state of 0. It's bonded to an atom with equal electronegativity. And in the product, hydrogen has an oxidation state of -1, or excuse me, +1. Hydrogen has lost electrons in the process. Hydrogen has gone from a 0 oxidation state to a +1 oxidation state because carbon has gone from -1 to -2.
Mm-hmm.
So they have reduced and oxidized each other. Carbon becomes more negative, hydrogen becomes more positive.
Yeah.
So what's OChem 2 really like?
Hell, no.
Okay.
It depends on what professor you have, I think, really. But it is OChem 1 is like learning the language, learning the alphabet, learning sentence structure. OChem 2 is writing essays. You're just learning a bunch of reactions, learning a bunch of mechanisms, learning a bunch of multi-step synthesis skills.
Does it become more intuitive as you go along or not?
That's the goal. Yeah. The goal is for it to become more intuitive, but it's not. It doesn't always happen. I have OChem 2 students that I've had in OChem 1, and I have a lot of OChem 2 students that I have had different professors. And even the students that had me for OChem 1, they sometimes struggle in OChem 2 because there's just so many reactions to know. And if you studied this for a year or 2 years, or if you stood up in front of people 3 times a year for 4 years, then it would become very intuitive. But when you're studying it over the course of a few months, it's hard to be familiar enough with it for it to become intuitive. Some people get it, and I think the people that do get it have flashcards, and they do a lot of practice and a lot of reviewing. I think you've heard the saying that some professors just lose touch with how challenging their topic can be because that's all they think about anymore. That's all they do. So of course it becomes intuitive for them, The challenge for them becomes staying in tune with how hard it is to be a first-time learner. I used to never teach a section like this, overview of organic reactions. I will never not teach it anymore because I find it so helpful for breaking down what you're going to see going forward. The only thing I think I still need to improve on is getting you guys examples of reactions that are out in the literature.
I just wonder if it's like, I'm trying to like compare it to like calculus.
Calculus?
It gets to a point where certain like integrals, stuff like that, you should just recognize.
Yes, if you do it enough, you should start to recognize them.
You know, like, I mean, it gets to a point where you realize that the integral of 1 over x is ln. You have to realize that and keep going through it.
Yeah.
And like, you can use that, like, if it's combined with something else, use that prior knowledge to make it easier to solve another question with that included into it. That kind of thing. That's good. That's what I'm kind of comparing it to.
I think that would be my end goal, would be for you guys to be able to see it and then say, well, I know what reagent needs to be there. I know what type of reaction is happening. I can see that rearrangement occurring, so I know that that must be important. Do you know what I used to do to come up with things for my like exams? I would go to the FDA page and I would find compounds that had been recently synthesized or like important compounds, and then I would just include those. Ask about its functional groups, ask about chiral carbons, ask about a synthesis route, you know? But it's not super easy to always find meaningful ones. Oops. So I don't know that this is even the FDA. One of the reasons, though, that I rely so heavily on bond line structure is because that is how I have seen most chemists report molecules. And I want you guys, I know most of you guys are not chemists, so you're not going to be spending time looking through the chemical literature. But I do want you, if you ever stumble across chemical literature, I want you to say, yeah, I know some of those words. Like this is syntheses of different compounds. I don't know. Anybody know vonoprazan? Because that's how you make it. You'll also notice the reactions I'm going to teach you in these coming weeks. You'll almost never see them on here. And that's because we are learning introductory chemistry. So we're going to learn like the simple things. This is like leading edge chemistry. I don't know, maybe this is a bad example, but if you become an organic chemistry student, an organic chemistry graduate student, these are the types of compounds that you're going to need to know. They're just not that useful for us in this context. So we just don't get into it too much. All right. Questions so far on types of reactions, classes of reactions, how to identify them? Can you look at this and tell me what class of reaction has occurred? Let me try to zoom in there. Oops, sorry, that is the most I can zoom in. Right here. Substitution. Ester substituted for a ketone. No pi bond consumed, just bonds that were swapped. Okay? See if I can find you guys a better one. Ah, right here. You guys know this group, this functional group? Two names for it. Cyano, nitrile. So that's the CN triple bond. Look at what happens over here. Where did the C go? It's still there. It's just not highlighted anymore because now it's shown with bond line structure. What type of reaction has occurred? Not substitution. It is reduction, which is not enough. That's true, but what class? It is hydrogenation, reductive hydrogenation, which is a term that what textbooks use. Addition, elimination, or substitution? It's not substitution. It's addition because pi bonds are being consumed. CN triple bond comes down to a CN single bond. Where did the pi bonds go? Hydrogens were added across them. And look at what's added. Hydrogen, hydrogenation, plus nickel. Did you know that nickel and palladium are in the same family? So they both help catalyze those reactions. Boy, you know, I'm so embarrassed. I am second guessing myself that nickel and palladium are in the same family. It's okay. I took inorganic chemistry once, so. All right. There's a few other pieces of terminology that I want us to talk about when it comes to organic reactions. But I will say, looking at the transformation and identifying what type of reaction has occurred is very important. Actually, there's a tricky one we're going to look at this semester, and I want you guys to take a stab at this. Classify it. I'll tell you what, it's neither oxidation or elimination. It doesn't oxidize or reduce. Pi bond is consumed, right? There were 2 pi bonds, now there is 1. Confusingly, both of the carbon-carbon pi bonds are gone. Correct? Instead, a carbon-oxygen pi bond is left. So oxygen was added to the compound. So were 2 hydrogens. So there is addition of those new groups and the consumption of a pi bond, but the pi bonds kind of rearrange and they shift. Or let's look back at the one of the early reactions I showed you guys, the Diels-Alder reaction. How would you classify this? Addition. 1 equivalence of addition or 2 equivalents of addition? Confusingly, this is 1 addition of, or 1 equivalence of addition. There are 3 pi bonds in the starting material, 1 in the product. However, there are 3 degrees of unsaturation in the starting material, 2 degrees in the product. One of the pi bonds has kind of been transformed into a ring. So its degree of unsaturation is preserved even though the pi bond has been consumed. So we call this a cycloaddition reaction, which helps to clarify the confusion about why 2 pi bonds are gone and why a ring has formed. Okay, good stuff. Yeah, you know what? That is, here's another one that you guys make some really good points. Let's look at this one. Oh, sorry, not you guys, the voices in my head that are telling me the reactions. Addition, substitution, or elimination? Pi bond is consumed, right? Yeah, all of our addition reactions change things. They all create new bonds. Question is, do I just have a bond and then I substitute it, you know? The confusing thing here is that it's not two groups that have been added, correct? It's one group that has been added. Both carbons bond to the same group. This is what functional group? Not quite an ether. Epoxide. It is kind of a more specific subclass with unique chemistry to other ethers. So the epoxide doesn't add two groups. The two groups are the same group. It's just one atom. But the pi bond has been consumed, but degrees of unsaturation stay the same. So we still consider it an addition reaction, even though the degrees of unsaturation haven't changed. I think I might have told you guys this early on in the semester when we were talking about polar bonds. We are the ones trying to put nature into boxes. So be comfortable with the fact that nature is going to break outside of the boxes a little bit. I'm not going to try and quiz you and test you and trick you in ways that make you wonder, is nature unhappy with the box that we put it in? Does that sound good? Let science do what science wants to do. We'll do our best to apply rules and names so that we can communicate about it as best as possible. Good stuff? It is good stuff. Okay, some other things to learn about reactions. I don't know that I want to call these classes of reactions so much as types of reactions. I know that sounds pretty much the same. We're just going to look at a couple of different terms here. First, we have polar reactions. Polar reactions typically involve an electrophile and a nucleophile. I'll spell them out for you guys, but this is how I will abbreviate them throughout the semester. Help me remember which one does what in a reaction. Sorry?
File means level,
That's true.
so the positive is the electrophile.
Loves positive charges.
Electrophile. I mean, it loves negative.
Loves electrons. Good. So this is our Lewis base. Another word for this is electron pair acceptor. Why is it an electron pair acceptor? Because it has a positive charge, or a partial positive charge. It is the positive end of a magnet, drawing in the negative end of a magnet.
That's the positive one.
There you go, yeah. And it is. That's why I abbreviate electrophile with the E+. Not that it has to be a full positive charge. Nucleophile. In other words, Lewis what? Lewis acid. Electron what? Donor. Something that uses its pair of electrons, be it a bond or a lone pair, uses its pair of electrons to form a bond with the electrophile. All of the reactions that we have seen so far were polar reactions. 95% of the reactions that we'll cover this semester are polar reactions, even in all of OChem 2 as well. The other class is just best called radical reactions. These involve homolytic cleavage. So there's not one atom that uses its pair of electrons to do something. It's not pairs of electrons doing things at all. Do you guys remember homolytic cleavage? Did you learn that in general chemistry? It's when a bond, two electrons, cleaves homolytically in equal directions. Polar reactions, their bonds cleave heterolytically. One atom takes the electrons from a bond. Which atom takes the electron when a bond breaks? The more partial negative atom. In a radical reaction, you can still make some predictions about what's going to happen with bond breaking and bond forming based on partial charges, but electrons do not move as pairs. They move as individual radicals. One of the reactions that we will use for this that is very helpful in organic synthesis, start with, say, an alkane, and end with an alkyl halide. Alkanes don't really do anything in terms of reactivity. Alkyl halides are great starting materials for doing organic synthesis. That's a good point. So this is Br2, and this is light. That's Planck's constant and frequency. So h nu. You can just draw it as a little v, or you can just put light. It's more often ultraviolet light. What type of reaction is this? What class, I mean? Substitution. No pi bonds involved anywhere, correct? So this is a substitution reaction. This is better called a radical substitution reaction. You guys have already seen arrow pushing on your midterm exam, and we're going to do a lot more arrow pushing. I'm just going to give you an example here of some radical arrow pushing. Have I shown you this yet? No. Radical reactions take place in 3 steps. Initiation. This is where a non-radical species homolytically cleaves its electrons, or cleaves its bond, and creates 2 radicals. You initiate radicals. The second step of a radical reaction is propagation. This is where one radical reacts with a non-radical to form a new non-radical and a new radical. And I want you to think about what you think propagation means. I propagate my plants. I take one plant and I propagate it so that I have 20 plants, and then 10 of them die. But I think of propagation as increasing in number. Propagation here is transferring. Number actually stays the same. So one of these bromine radicals interacts with the hydrogen on that carbon homolytically. I want you to notice something about my electron arrows. This is not a full-headed arrow. Full-headed arrow means 2 electrons. How do you indicate 1 electron? Fishhook arrow. A one-sided arrow. Not a full arrow. Not a full arrow. Not a full arrow. Not a full arrow. Notice that these 2 fishhook arrows are coming at each other. So what happens when 1 electron and 1 electron come together? A bond is formed, correct? 2 electrons create a pair. 1 electron going to the carbon. Propagation here creates a carbon radical and HBr. propagation. One radical becomes a different radical.
So your arrow from BR and from the CH bond are going to a point in space where the
Yes. And it's really awkward to show it because it doesn't matter where that point in space is. You just want to show those two radical arrows coming together. What do you think is easier? Polar reaction arrows or radical reaction arrows? At least all you have to do is move a pair all at once, and you don't have to take pairs and break them up and show them with half arrows. The last step in a radical reaction is called termination. What do you think happens in a termination step? Come on. Sure, you get your end product. You cleave something. Cleave what? This was homolytic cleavage in initiation. Heterolytic cleavage happens in polar reactions.
You join the radicals.
Join the radicals. If initiation is non-radical becomes two radicals, termination is two radicals become non-radical. Bromine radical bonds with carbon radical. So my final product is 2-methyl, 2-bromo-butane, and HBr. Coming back to this generic reaction I showed you before, I didn't give you the byproduct, did I? We said that it was substitution, but we could have also predicted the remaining Br and the H that was substituted can join up together. These are the steps that this reaction must go through. You don't take 2-methylbutane and make 2-bromo-2-methylbutane just like that. You have to first homolytically cleave the bromine bond, take a radical to steal the hydrogen, and then terminate the carbon and bromine radical. This is what we call the mechanism. This mechanism is 3 steps. 3 steps of bonds forming and bonds breaking. No more, no less. And there will be mechanisms that you will have to show me on unit tests and exams. You'll need to know how many steps there are. I'm going to walk you through that. You combine steps, you show bonds forming and breaking at the same time. You're supposing that something happens that doesn't happen. Some reactions happen in 1 step. Their mechanisms are 1-step mechanisms. Some mechanisms, several steps. Some mechanisms are 2 steps, but they have 4 resonance intermediates that all need to be shown. That happens much more in OCHEM 2. So tomorrow, there is a little bit more I want to talk to you about with reactions, organic reactions. I want to talk to you about energy, and I want to talk to you about transition states and intermediates. But it should be pretty simple. And then the rest of tomorrow, we're actually going to take a little breather from reactions. We're just going to talk more about alkenes, nomenclature, and reactivity. And that's going to set us up for next week to just be reaction after reaction after mechanism after reaction. All right? Okay, have a good night, guys. I'll see you tomorrow.